All right, welcome. Today, we are going to pull back the curtain on a core math concept that is, believe it or not, shaping the world all around us. We're talking everything from the arc of a basketball shot to the shape of a satellite dish. So let's just dive right in.
So, have you ever really stopped to wonder why that is? Why a basketball shot, or water from a fountain, or even just a crumpled piece of paper you toss at the bin? Why do they all follow that same perfect, graceful curve? It's definitely not a coincidence, and it's not magic. It's math, and the special kind of equation that describes this exact shape is exactly what we're going to get a handle on today.
So what do we call this thing, this powerful piece of math? Let's break down what a quadratic equation really is. And I promise you, the main idea behind it is way simpler than that name makes it sound. Okay, before we get all formal with the math, let's just strip away the jargon for a second. At its absolute heart, a quadratic equation is all built around one simple action, squaring a number, multiplying it by itself. That's actually where the name quadratic comes from. Think quad, like a square. So the equation is basically just a puzzle, asking us, hey, what number can I square, then maybe add or subtract a few other things to get this one specific result? And here it is in its official uniform, ax squared plus bx plus c equals 0. Now, it might look a little intimidating, but the absolute star of the show here is that x squared term. That tiny little 2 is the engine that creates that beautiful curve we keep talking about. It's so important, in fact, that the number a right in front of it can be anything except 0. Because think about it. If a were 0, that whole x squared term would just vanish, and we'd be left with a simple straight line, not our awesome curve.
So, we know what a quadratic is. The next logical question is, how do we solve it? How do we actually find that hidden value of x? Well, think of it like opening up a toolkit. There isn't just one way to do it. There are a few different tools we can pull out, and part of the skill is just knowing which tool is the right one for the job.
Okay, the first and, when it works, the fastest tool in our kit is called factoring. It's based on a really clever idea. If you multiply two things together and the answer is 0, well then one of those things has to be 0, right? So our goal is to just rewrite our equation to look like something times something else equals 0. So for this one on the slide, x squared minus 5x plus 6 equals 0, we're on the hunt for two numbers that multiply to get a positive 6 and add up to a negative 5. After a sec, you realize, hey, it's negative 2 and negative 3. So we can rewrite the whole thing as x minus 2 times x minus 3 equals 0. And for that to be true, either the first part is 0, meaning x equals 2, or the second part is 0, meaning x equals 3. Boom! We've got our two solutions.
But here's the catch. Factoring is kind of a specialized tool. It really only works for these nice, clean equations. What happens when you run into something like this? X squared minus 2x plus 2 equals 0. Go ahead, try it. Can you think of two numbers that multiply to positive 2 but add up to negative 2? You can't. It's just not possible. Our factoring tool is basically useless on this puzzle. Now, there is another manual method called completing the square that always works, but it's a bit of a grind. So when our simple tool fails, it's time to reach for the ultimate power tool.
And this is it, the master key, the quadratic formula. I know it looks a little scary, but this right here is one of the most powerful formulas in all of algebra. It is the universal solvent, the tool that will crack any quadratic equation you throw at it. No exceptions. You just have to figure out your a, b, and c from the equation, plug them in here, and it spits out the answer. Every single time.
So we've found these x values, right? Like the 2 and 3 from our first example. But what do those numbers actually mean? They're not just random answers to a puzzle. They represent real, actual points on a graph. And this is the cool part, where we connect the numbers to the picture, and we see how this algebra creates that beautiful curve we started with, the parabola. Okay, let's go back to our master key for a second, the big formula. See that little piece tucked away under the square root sign, the b squared minus 4ac? Well, that little chunk has a special name. It's called the discriminant, and it's basically like a crystal ball. Before you even bother solving the whole thing, you can just calculate this one little part, and it will tell you exactly how many solutions your equation is going to have. It's an amazing shortcut. And this table right here shows us the 3 possible futures our crystal ball can predict. If the discriminant, d, is a positive number, that tells us our parabola is going to cross the x-axis in 2 different spots, so 2 real solutions. If d is exactly 0, the parabola comes down and just kisses the x-axis at its lowest point. That's one solution. And if d is negative, Well, you can't take the square root of a negative number in the real world, which means our parabola completely misses the x-axis altogether. No real solutions to be found. Another key secret of the parabola is simply which way it opens. And you know what? The rule for this could not be easier. It all comes back to a, that very first number in our equation. If a is a positive number, the parabola opens up, like a smile. If a is negative, it opens down, like a frown. And that smile or frown has a really important feature, its lowest or highest point. We call that the vertex. It's the turning point of the whole curve, and it is incredibly useful for solving real-world problems. Okay, we've covered the theory, what a quadratic is, how to solve it, what its graph looks like, but the biggest question is always, yeah, but when am I ever going to use this? Well, let's find out. It's time to take our new toolkit out into the wild and see what it can do. So imagine this. You've got 20 feet of fencing and you want to build a rectangular garden. You can make it super long and skinny, right? Or you can make it short and wide. But which shape, which dimensions will give you the absolute biggest area for your plants? This is a classic problem. How do you find that perfect sweet spot without just guessing all day? This is where we turn the word problem into a quadratic equation. We know the perimeter is 20, so 2 lengths and 2 widths add up to 20. That means 1 length plus 1 width has to be 10. So if we just call the length x, then the width has to be 10 minus x. Now area is just length times width, which gives us a equals x times 10 minus x. When we multiply that out, look what we get. A equals negative x squared plus 10x. There it is, our quadratic. And remember what we just learned? Since a is negative 1, this is a downward-facing parabola, a frown. And asking for the maximum area is the exact same thing as asking what's the highest point of that parabola, which we know is the vertex. And luckily, there's a handy little formula to find the x value of the vertex. It's just negative b divided by 2a. In our area equation, b is 10 and a is negative 1. So we plug that in. We get negative 10 divided by 2 times negative 1, which is just 5. So the perfect length is 5 feet. That means the width is 10 minus 5, which is also 5 feet. A perfect square gives us the biggest possible area of 5 times 5, which is 25 square feet. Math just designed the perfect garden for us. So there you have it. In just a few minutes, we went all the way from a simple question about why a basketball flies in an arc to defining, solving, and graphing these powerful equations. We even used one to optimize a real-world problem. The big takeaway here is that these equations aren't just for a math classroom. They're a language for describing and improving the world all around us. And now, to wrap things up, a final challenge to test out your new skills. Here's the equation. Y equals x squared minus 6x plus 13. So first question for you, is this parabola a smile or a frown? And knowing that, can you use what you now know about the vertex to find its absolute minimum value, the lowest point it will ever reach? All the tools are in your toolkit now. Thanks for watching. Hey, welcome. Today, we're jumping back into a bit of math, but we're seriously leveling up. We're going to crack the code on those more complex equations. You know, the ones that go way beyond the basics you remember from school. All right, let's get right into it. So we all got pretty comfortable with x squared, right? You know, it gives you that nice, predictable, U-shaped curve, the parabola. But what happens when you run into something like x to the power of 5, or 7, or even 10? Suddenly, the graphs get kind of wild, the solutions get a lot trickier, and that's exactly what we're here to figure out. That's right, we are officially leaving that simple little parabola in the dust and stepping into the much more interesting, way more dynamic, and frankly, squiggly world of higher degree polynomials. And this is less about just memorizing formulas and way more about becoming a kind of math detective. And you know, any good detective has to know what clues to look for. So in this first part, we're going to learn how to spot those absolutely essential pieces of information that are hidden inside every single one of these equations. These are the clues that are going to tell us everything we need to know. First off, what even is a polynomial? Let's just keep it super simple. Think of it like a math recipe. You've got some powers of x, you multiply them by some numbers, and then you just add or subtract all those pieces together. The only real rules: you can't divide by x, and you can't have things like the square root of x. That's pretty much it. Now, here is the single most important clue you can find. It's called the degree. And that's literally just the highest power of x that you see in the entire equation. A degree of 2 is a quadratic, a 3 is a cubic, 4 is a quartic, you get the idea. This one number gives us a massive, massive hint about how the whole thing is going to behave. And here's exactly why that degree is so important. A polynomial with a degree of, let's say, n, can cross the x-axis at most n times. So a cubic equation, one with an x cubed in it, can have at most 3 solutions. A quartic can have up to 4. This rule basically sets the boundaries for our whole investigation. So we're talking about roots, but what is a root anyway? Well, a root is just a number that you can plug in for x that makes the entire polynomial equal exactly 0. That's it. It's the solution to the puzzle, the number that makes the whole equation work out perfectly. And if you look at a graph, this becomes super, super obvious. Forget all the abstract algebra for a second. Visually, the roots are just the points where that curvy line crosses, or maybe just touches the horizontal x-axis. Every single one of those spots is a solution. Okay, so we've gathered our first clues. The degree tells us the maximum number of roots we can have, and we know those roots are where the graph hits the x-axis. Now it's time for the secret key, the thing that connects all of this together. I mean, this is the big question, right? For some really complicated thing like an x cubed or an x to the 4th equation, how in the world do you actually find those specific points? Well, it turns out there's this really beautiful, almost magical connection that we can use. So let's say we're just testing a few numbers. Maybe we try plugging in x equals 2, and what do you know? It makes the whole polynomial equal 0. Great, we found a root. So what does that actually tell us? It tells us that, without a doubt, the term x minus 2 has to be one of the building blocks, what we call a factor, of our polynomial. This is the big secret, the factor theorem. If you know a root, you automatically know a factor. And if you know a factor, you know a root. It's this perfect two-way street, and it is the master key to breaking these big polynomials down into smaller, manageable pieces. Let's actually see this in action. We've got this cubic here. We can test a simple number like 1. And bingo, it works. The whole thing equals 0. So since x equals 1 is a root, we know that x minus 1 has to be a factor. The next step is to use that to simplify the problem. We divide our big cubic by x minus 1, and what's left is a much friendlier quadratic. And from there, factoring the rest is easy. And just like that, by finding just one root, we found all 3. 1, 2, and 3. We cracked it. So we figured out how to find the roots algebraically. But what do all these clues tell us about the actual shape of the graph? Let's connect the algebra to what we see visually. Okay, check this out. Not all roots behave the same way on the graph. If you have a simple root, one that just appears once, the graph will slice straight through the x-axis at that point. But if you have what's called a repeated root, say from a factor like x minus 2 squared, the graph does something different. It doesn't cross through, it just comes down, gently touches the x-axis, and then turns right back around, kind of like a bounce. We can also predict where the graph is heading in the long run, what we call its end behavior. For any polynomial that has an odd degree, like x cubed or x to the 5th, and a positive number out front, the graph will always start way down on the bottom left and then shoot off to infinity up on the top right. And for the other case, polynomials with an even degree, like our old friend x squared or something like x to the 4th, if they have a positive lead term, both arms of the graph will point in the same direction. They'll both point up, starting high on the left and ending high on the right. It'll look kind of like a U, or maybe even a W. All right, time to put it all together. We've got our clues, we've got our secret key, and we know basically what the final picture is supposed to look like. So let's solve one more puzzle, this time from start to finish. Here's our final cubic. Now, instead of guessing roots, we can use another cool trick here called factoring by grouping. Watch this. We group the first 2 terms together and the last 2 terms together. From that first pair, we can pull out an x squared, and we're left with x plus 2. From the second pair, we pull out a -1, and we're also left with x plus 2. And since both parts now have that common x plus 2, we can just pull it out to the front. What's left over is x squared minus 1, which is a classic difference of squares that's easy to factor. And there they are. Our 3 roots are -2, -1, and +1. The code is cracked. So there you have it. You now have a complete toolkit. First, always look at the degree. That tells you the maximum number of solutions. Second, remember that incredible link between roots and factors? It's the key to breaking the problem down. And third, use the clues about end behavior and how the roots cross or touch the axis to sketch a picture in your mind. With these keys, no polynomial is too intimidating. And with all that, I'm going to leave you with one final challenge.
Take a look at this equation. Because it has an odd degree, that x to the fifth, we know it has to cross the x-axis at least once. But how could you actually prove that it crosses exactly once? Think about the tools we just talked about. A full formal proof takes a little bit of calculus, but you can get surprisingly close with just the logic we've built today. Give it some thought. Thanks for joining me on this math investigation.